My name is Christian Avalos, and I'm from Mercer Island, Washington.
My name's Noah Witkowski, and I'm from Wheatfield, Indiana.
My name is Matt Sal Kelly, and I'm from Long Island, New York.
My name's Sam Chevay. I'm from Chicago, Illinois, and along with the help of Professor Hahn, we were able to perform research this summer on improving the technology of 3D cell culturing.
So diving into our presentation a bit, the main areas we hope to cover with the presentation include the introduction, design challenges, determining appropriate materials and manufacturers, and a recommended design. A new, more advanced technology has emerged involving analyzing cells in a 3D sense. This allows for drug discovery, cancer research, and treatment planning at a higher level. 3D cell culture models are emerging as it has a much higher throughput than old traditional methods. Though current models are lagging, as a group, the problem we were tasked with was determining the materials and manufacturing methods that align with the design constraints. In addition, improving or altering the design to improve the product. When creating and looking at the product, there are several parameters we must meet. The first is to match with a 96 well plate and needs to be done in an 8x12 array. To improve the throughput, it must be done in a single stroke and the process must be completely automated. Lastly, since we are involved with chemicals, it must meet all biocompatibility standards. Pictured above is the initial design that Professor Hahn and his team made. The design met specifications, though manufacturing was quite difficult, as we explained later in this presentation.
There were three key challenges in the current design of the product that we needed to consider throughout the course of the project. First, the ability to mass manufacture units of the product effectively. Second, determining a material that meets the design specifications for stress and strain, as well as biocompatibility and chemical inertness. Finally, the product needed to be more user-friendly to promote higher throughput and production. The original design was found to be difficult to manufacture using traditional mass production methods. Prototypes were easily 3D printed, but the thin components of the material made it difficult to manufacture using other methods, particularly injection molding. Our challenge was to find a new method that would better suit the current design or adjust the design to better fit the injection molding option. Compatibility of the material for the mesh component is vital to the success of the product, as this device is exposed to a variety of chemical substances during organoid culturing. Requirements included chemical inertness and biocompatibility, adding a new consideration for manufacturing methods and materials. User efficiency is a core aspect of the design that needed to be improved. As shown in the video, the separation of the mesh from the spacer grid is a hassle, taking approximately 15 seconds and requiring manual pushing around each edge of the device. Our challenge was to find a single contact method to separate the mesh from the spacer grid, with the potential for automation in the future. With the primary function of the design to decrease the time to process organoids during culturing, this was a crucial improvement to make on the original prototype.
For our connector material, we chose a Shore 25A liquid silicone rubber. It has a 500% elongation before fracture and is biocompatible with both UV and ozone sterilization techniques. For the ejector and spacer grid material, we chose LDPE. It is a commonly injected molded plastic and is also biocompatible with UV and ozone sterilization techniques. Our manufacturing plan is to use an injection molding manufacturing process for the spacer grid, the separator, and the connector. And we decided in order to ensure quality, we should seek out two manufacturers, one that specializes in LDPE injection molding, the other one that specializes in liquid silicone rubber injection molding. So far, for our LDPE manufacturer, we've found CKK Automation. They are currently willing to create prototypes for the separator and spacer grid, and we are actively communicating with them about quotes and pricing. On the LSR manufacturing side, we found Advanced Prototyping Modeling. Originally, they were very interested in manufacturing prototypes. Since then, they have not been responding to our communications.
Our recommended design is the guide rails and presser design. This design reduces the amount of time it takes to release the connectors from the spacer grid. Guide rails have been added to the separator to allow the user to line up the pegs with the holes. A new third part made of LDPE, called a presser, has also been designed. After the spacer grid has been placed on the separator, the presser releases the connectors by pressing the two together. This design, we estimate, would reduce the amount of time it takes to release the connectors from 15 seconds to about 5 seconds. A drawback of this design is that more plastic would be used, meaning that the cost would increase. Here are the three parts shown separately. Here are other designs we created that may be worth prototyping in the future. This mesh redesign would be easier to manufacture due to the larger amount of surface area it has. We also considered the spring-loaded spacer grid as an alternative method to releasing the connectors. Thank you for taking the time to listen to our presentation.